here, and you get these rings. These are called sundogs, and you get all kinds of complicated patterns of this reflected sunlight when you have cirrus clouds, and you get, of course, different kinds of shapes of ice crystals, and they lead to all these different patterns here. So once again, if you give me the phase function, I can predict these sorts of things. And then the next thing to do is understand the physics of what caused this bump and this one and this one. Okay, so the things to remember are simply that the VSF is parameterizing all the complicated physics and putting it into one nice simple curve, so you don't have to deal with diffraction and reflection and refraction and so forth. It's really all we need to compute the unpolarized scattering. Now, if you have polarization, then you're going to have a phase function for each of these different things. One would be taking unpolarized light to unpolarized, that's these things. But then if you have vertical to horizontal, or you have vertical going to right circular, or right circular going to left circular, whatever, each of those basically has a phase function. And those are the elements of the Mueller matrix that you're going to learn more about from Ken next week. Okay, so the magnitude of the VSF, or the scattering coefficient, depends strongly on the concentration of the particles. That's our guy flying the airplane, and the you change the size of the particles, so it really changed the scattering coefficient. That's the concentration. We went from a lot of small particles to a few big ones. The shape of the phase function is once again determined by the particle size, shape, internal structure, etc., and that in general depends on wavelength. Although there's very little data of phase functions measured at different wavelengths. Like this Ukrainian instrument that I showed you, the data that Emmanuel gave me, that instrument only works at 530 nanometers. So what would those curves look like at 400 or 700? Well, don't know, hasn't been measured. Okay, and keep in mind here, we're only talking about unpolarized light, and we're talking about isotropic media. That means the optical properties are the same in any direction. It doesn't mean the individual particles are spherical, they're just randomly oriented. When you get in a cirrus cloud, if it's calm and those ice crystals are settling down, they all may take kind of the same orientation, and then the optical properties will be different in one direction than they are in the other. But that doesn't usually occur in the oceans. Okay, so next up we'll talk about models for scattering. Do we need to take a 5-minute bathroom break here? We're basically half done with the lecture. So, bathroom break? Okay, let's do it. And then come back at, let's say, 20 till, so that's 6 minutes.
So the VSF that you showed for ice crystals,
yeah,
that's for randomly oriented ice crystals? Does that assume some orientation?
Yeah, I think that's, let me think. I think what it is I'd have to go read the paper. They took like a hexagonal crystal, and they probably oriented it like horizontally, but then they rotated it, and then they ran the light in sideways, and they ran it in parallel to the axis and so forth. I'd have to look to see.
Rotation in one direction.
Yeah, I think so. Because if in a normal cirrus cloud, there's ice crystals, but they're all randomly oriented, then you don't get the sundogs and stuff.
Okay.
It's only if it's calm air and they're settling and they take a preferential direction, and then they'll still be rotating this way or this way, but not this way, and then you can get these various peaks. They'll come and go depending on the shape of the crystal and the orientation. Yeah.
Cool. Thank you.
Did anybody stop the recording so we don't talk about random things on?
Okay. Let's see.